Alright, so what else we got? Shout them out. Things we talked about in lab, things you've heard me say. We got a few more for each here. Evidence of a physical change, evidence of a chemical change, or examples. Either one.
Smoke.
Good, smoke produced. You see smoke, that is evidence of a chemical change. Before I ask for more examples, solubility, what's another word for that? Dissolving. Make sure we write that down. So salt is soluble in water. Sugar is soluble in water. Sand is not soluble in water. Meaning, salt and sugar will dissolve. Sand will not. Put sand in water, you can stir it up for 100 years. It will not dissolve at all. In fact, the water would evaporate before you're done stirring that up. All right, what else? Shout them out. You don't have to raise your hand. Other physical, chemical. Use your homework. Look at the worksheet. Use that homework that was due yesterday for ideas. We've gone through this in lab. Let's go. We gotta get more vocal in here.
Smell.
Sleep. What?
Smell.
Smell. Okay.
Chemical.
Yeah. So odor change. We're gonna make sure it's underlining that word change. Again, like this banana has a smell. It smells like a banana, right? I don't know how else to explain that, right? So it has an odor to it. Me smelling it doesn't change it, so that's physical. So if I just say, oh, this has a certain smell, so I'm not going to write it because I don't want to confuse you, but if I just wrote odor over here, that's physical. You can observe the odor of something and it doesn't change. But if I lit this banana on fire or burned it, it might start to smell different. That's going through a chemical change, right? So odor change. What else?
Rusting.
Rusting. Can I just put a general statement? Color change? Color change. Leaves are changing colors. And they die and they fall on my lawn and I have to rake them. And I can't stand doing that. There's a few things in this world that really irritate me that I have to do. Raking up leaves, painting, vacuuming, making the bed. Not a fan of that. Who makes their bed every day? Just one person? Everyone else is lying, Steve. You guys, your bed's just trash all the time? I'm being recorded here, so I'm not going to call out my wife, but she's got to have it all nice and neat before we leave in the morning. I'm like, we're just going to get it all screwed up again later. What's the point anyways? Back to this. Why was I talking about that? What did you say? Rusting? Color change? What else? Why would I start talking about it? Leaves! I forget what the train of thought there. Leaves. So leaves, color change, right? And then they fall off, and then you gotta pick them up, or else your grass dies. Anyways, what else?
Hardness.
Melting. Someone else said something.
Hardness.
Yeah, how hard something is. So, Paige said melting. I could list all of the what changes. What are those called?
Physical change or no?
Yeah, you're on the right track. Phase change. Phase change. So, I guess I can write all the words here, you know, because it's early in the year still. So, melting, freezing, boiling, condensing, subliming, deposition. Sorry, that's really messy. So melting, freezing, boiling, condensing, subliming, deposition. Notice it's the opposites I'm putting as well, right? So melting is solid to liquid. Freezing, liquid to solid. So those are opposites. Boiling is going liquid to gas. Condensing, gas to liquid. Subliming, solid to gas. Deposition, gas to solid. So any phase that's changing into a new or different phase, all physical, right? Because if you have particles very close, is this on the screen?
Yeah.
Particles very close together, and we're going to talk about this right after these notes. That's a solid. Well, if you heat that up, and they start turning to a liquid, and then eventually a gas, what do the particles do? If they go from a solid to a gas, subliming, what do those particles, if I was going to draw it, what would they look like?
Spread out.
Spread out, right. So the particles would be more spread out, right? So if this is one particle of water, this is the same particle. It's just not close to its neighbors here, or its friends, or whatever you want to say. It's still water, right? So I really make sure I kind of focus on that and say that a lot early in the year. That is definitely physical. When you just move the particles closer or farther apart, you're not changing what it is. You're not changing composition. Okay. All right. What else? There's other ones here over here that we got to get. You got all the big ones. These right here. Well, and that. So melting, all the phase changes. That, and I would say that. Those three. I know there's 4 arrows, but I should have wrote that here. So all the phase changes, that's really something common you need to know. Dissolving, that's physical, you need to know that. And density, calculating density, observing density. Those are the big Regents things. And that kind of covers everything in real life you would really see anyway. Either it's changing phase, you're making a solution, or a density type situation. Not much else we're going to be doing in real life, like in lab and stuff. All right, anyways, chemical, let's get the rest done here. Think of the demos you saw. What things did you see? The first 3 demos with sodium, potassium, magnesium. All 3 showed these 2 things you haven't said yet.
Heat.
Okay, 3 things. Heat produced. Heat produced or absorbed. Go to Walgreens, Rite Aid, whatever, grocery store. You get a cold pack, but it's not cold yet. It's at room temp. What do you have to do to make it cold? You guys know what I'm talking about? They're like, it has like gel in it, or sometimes you shake it and you can hear like particles, little solids bouncing around in there. You guys all familiar with this? Most of you, okay? What do you do to make it cold usually? What's that? No, I'm talking about the one where you don't need to put it in the freezer. It's just, it's a chemical reaction. Yeah, you squeeze it or snap something inside of it. Anyone familiar with this? You seem like you are, okay? So, that's absorbing heat from you, right? If it's getting cold and you touch it, it's taking the heat from you. So that's definitely a chemical reaction. The hot packs that some people might use. All right, I know hunters might use them, right? If they're out in the winter or whatever and their hands are freezing, their feet, it's normal room temp, and then they squeeze it or break it and it gets really, really hot. Put it in boots or gloves or whatever, just hold on to it. All right, some of them are called like hot hands. So anyways, that's a chemical reaction too, because it went from being at room temp to giving off all types of heat. Why? Chemicals inside. All right, what else? 2 other things we gotta get. It's the most obvious. Besides that, fire also gives this off, besides heat. Light produced. You see light. And one more, it's kind of like smoke, but you can't see it. Smoke is like little tiny particles, that's why you can see it. Well, that's not a great way to say it. Smoke you can see because it's a little different composition than this other stuff that you really can't see, like it's in the air right now. Say it. No, air's made of it. The oxygen's an example of it. Gas. Gas produced. So, for chemical change, the biggest ones you need to really pay attention to: fire, light, gas produced, and then the color change. Those are the common ones that the Regents might focus on. All right? And the heat and absorbed or produced, that's a little bit harder. You'd have to either touch it or put a thermometer in it, right? Something could be really hot or really cold, and you just looking at it, you may not know. Okay? So, this over here will change the composition. You'll get new substances. All right, we should put that here at the bottom. New substances produced. You're making something new over here that wasn't there before, and you know what? It's not reversible. You can't go back. Like a leaf. Think about a leaf that's changing color. It's not going back to green. It's going to die. It's going to decompose. Okay? Here, physical, nothing new created. Nothing new created. Okay? And actually, I just reminded myself. There's a couple words I want you to add over here. Okay? I'll just leave that list there. Add this to the bottom. I just said one of them, decomposition, which means decompose, which means breaking down like roadkill, right? It'll eventually decompose, go back into the earth. Break down. Bacteria eats it up, basically. Okay, decomposition. Another word here, fermentation. What's that mean? Fermentation, what's it mean? You guys like apple cider? It's gonna be close for now. Maybe everybody's making that, selling that. Okay, if you buy apple cider and just let it sit for like weeks, months, it's gonna ferment. What does that mean? No one knows what ferment means? Fermentation? You awake, Jake? Did you have a coffee today?
No.
Oh, there you go. You're a little too young to be dependent on coffee. But no one knows what fermentation means. What? Yeah, rots, breaking down, good. But fermentation is a process that is I don't even know if it's a multi-billion-dollar industry or trillion-dollar industry. Makes a lot of money in this country and the world. Without fermentation, a lot of companies wouldn't exist and there'd be no money out of that product. And one could argue it should be illegal. Alcohol, right, so alcohol is made. Okay, fermentation. Fermentation is how you make alcohol. All right, apple cider will ferment over time and it'll get some alcohol in it. Okay? Decomposition, and there's a reason for that. It's because there's sugar in it. You need sugar for fermentation. So decomposition, fermentation. You said rusting. That's another word. Give me a word that, well, actually, only one metal rusts. What is it?
Iron.
Iron rusts. Nothing else. Now, that may or may not help you right now at this point in your life. What's another word for metals that look like they're rusting, but they're not rusting?
Oxidation.
Oxidation. Write that down. Okay. Right here. Magnesium. It has this like black coating on it. Okay. I can scrub that off with steel wool. That black coating is oxidation. If anyone wears jewelry, sometimes jewelry, silver, gold, gets kind of like dull. Almost like tarnished, right? You know the word tarnish means when silver gets like black? That's oxidation. You're not scrubbing silver with steel wool though. I wouldn't recommend it, but you can use chemicals that will react with that. Okay? Clean it up. One more word. Corrosion. What's that mean? Kind of like oxidation. Metals will basically deteriorate over time if they're exposed to water and air long enough. Corrosion. Acid can eat away at something. That's called corrosion too, sort of. I guess the only other word, there's one more word, sorry, decay. Right, so these two, decay and decomposition, are kind of the same concept. Things will break down. If I left this banana sitting here for a month, it would start to do what? What color would it turn after a month? It might be black at that point. It goes from green to yellow, because it's going through chemical changes, to brown, then the black. It'll literally decay and decompose right on the desk. Okay. So, I know I'm spending a lot of time here today on this, but it's really important you know the difference between physical, chemical, and some terms we're going to use this year. All right? Okay, now what I want to do is go through solids, liquids, and gases. We're going to go quick because you should already know them. And then that's probably going to be all the time we have for today. All right, states of matter. Here we go. States of matter. And like I said yesterday, we will go through the forms of matter. Elements, compounds, homogeneous, heterogeneous. We'll go through each one slowly to help you learn a little bit more. Yesterday was an overview, and the homework was to kind of get the ball rolling, right? But I want to go through the states of matter first, then we'll go through each of those slowly, all right? States of matter: solid, liquid, and gas. Okay. So solids have the abbreviation of an S. So let's say we had, we'll just go Cu solid, copper solid. Liquid would be like mercury, Hg, little L. Gas, we'll say neon, little G. So little S means solid, little L means liquid, little G means gas. Right? And then you could have compounds too, like solid water, H2O, S, H2L, H2OL, H2O gas. Okay, let's draw what we call particle diagrams of each one. Maybe I'll just show you. You draw it, I'll show you. Lights, please, Liz. So this may seem easy to some of you, or all of you, I don't know. But that's image of a solid substance. So notice particles are right on top of each other, basically touching. Solids are very close together, very orderly. What's that mean? Very ordered. Low entropy. All right, so not only do you need to know the definition of the word, but how to apply it. So solids have the lowest entropy because they're very orderly. Kind of like you guys right now. You're sitting fairly close in neat rows, and it's repeating. So that's a solid. Sketch that in your notes. Something similar. You don't have to do it, don't spend 5 minutes drawing it. But draw the particles close together. You don't have to show depth, right? So I guess I should show you what I mean. Just kind of draw the particles very close together, orderly, right? So something like that. I don't have them necessarily touching, and that's okay, as long as they're close and there's patterns, right? Straight lines, repeating pattern. That's a solid. What are they doing? What are those lines supposed to be showing? Vibrating. Write that down. Solids vibrate. Everything in the world, universe, I should say, is always moving. Constant motion. It's called the kinetic molecular theory. Everything is moving. Is this desk moving? No, it doesn't look like it, but it is. The particles in the desk are doing that. They're vibrating constantly. Okay, so solids do move. Doesn't look like it, but they are. They just don't move around, right? So like I could say, Liam, move. He could just flail about in his desk. Or he could get up and walk around. If he gets up and walks around, that's more like that, a liquid. Liquid particles. Now, I don't like this image for one reason, and that is, listen to me carefully here, look at me, stop what you're doing, this is important. Liquid particles don't really have any more spaces than solid particles. So in other words, these particles here with the big spaces, that's not really accurate. So again, eyes up here. So if we have two particles very close together, let's say they're solid particles, all they're doing is this, vibrating. If they become a liquid, what can they now do? They can move around. But they don't spread out really. Liquids and solids, as far as spacing between particles, really, it's the same. Okay, the spacing doesn't really change a whole lot. It's just liquid particles can flow. That's a word you should write down, liquids flow. Okay, they can move around each other. All right? But they really, it's not a great picture. So you might be thinking, why is he using that picture? Because it is good visually to see the difference. It's disorganized compared to a solid. So higher entropy, more disorder for a liquid. Right? So if I was going to draw a liquid, all right, in a box, let's say, I might just draw random particles. Okay? That doesn't look organized like a solid, right? So my solid was very organized, that's not, but they are still pretty close together. So that's how you would get credit on a test or a Regis, if they said draw a diagram of a liquid. And then a gas, okay, spread out. These lines indicate they're moving quickly because gas particles are flying all over the place. So how are you drawing gas particles in a box? All right, gas particles are very spread out. Okay, big, they fill their container, right? Solids and liquids would sit at the bottom, right? So if I had a big clear box on the desk and I poured just a little bit of water, the water would be at the bottom of the box, right? Solids would sit at the bottom. But if you put a little bit of gas or air into a box, assuming you could see it, it would fill the whole thing. The air in this room fills up the whole room. The air outside tries to fill the entire atmosphere. Gases are always expanding. Gas particles hate each other. That's my analogy. They hate each other. They want to get away, right? They want to fill their container. They want to fill their container. That's what's cool about gases. If I took this much gas, right? So let's say this was filled with oxygen gas, and then I open it up. So just this small amount, this is a certain volume. I think it's 1 liter, maybe more. 2 liters? It's not 2 liters. 1 liter. So if I open this up, the oxygen in here now will fill this entire room. So the volume of the gas changes, right? The point of the balloon was to show you air takes up space. Gases, their volume can change depending on the size of their container. If I take the same number of particles and put them in a bigger container, then the volume is that big. If I squeeze this into a smaller container, the volume is that big. So gas particles can expand and contract very easily. Whereas liquids and solids, these two, they can't expand or contract because they're too close together. They hate each other. They can't move very well. Okay? Gas, what do you think? High or low entropy? High entropy. Gases have lots of entropy because they're very disordered. Particles flying around, spread out. High entropy. All right? There's some notes that I want to actually, things I was saying, we're going to write in our notes tomorrow. Let me give you your book work and we're going to call it. We got a couple minutes here. Page 75. So it's in the book. So if you don't want to bring the book home, I would do it today in school, somehow, some way. Page 75, 1 through 4. Page 79, I'll text it and I'll put it in the box later. 10 through 12 and 14. All right. There is some other homework, but I'll give that to you tomorrow. All right, so that's it. There's not that many problems there. So that's due tomorrow. I don't really want you doing it in your notebook because I think it screws up your notes, right? I want notes to be just notes. So you can do that wherever you need to. I'm not going to collect it. I'll come around and check that you did it. If you want to do it in your notes, you know, whatever. I can't stop you, but I just don't recommend it. Notes should just be notes. All right, that's it. Bell's going to ring soon.